Constructing a massive, fully operational chemical facility from absolute zero on a blank plot of land presents a uniquely unforgiving engineering challenge. Upgrading an existing facility is called a brownfield project, where engineers face severe spatial constraints and high integration risks tying into old infrastructure. Before pouring a single yard of concrete, engineers face massive logistical hurdles. They have to develop the site topography, secure power and water utilities, and navigate complex legal permitting. To manage this scale, project teams follow a strict four-step chronological roadmap. The process flows from analyzing the spatial canvas to detailing the chemical logic, building a process safety shield, and finally managing the physical execution. If a project team skips or rushes any of these specific phases, they guarantee catastrophic physical or financial failure later on. Phase 1 is the canvas. Engineers rely on data-driven heat maps and scoring models to find the exact geographical location that supports the project's physical demands. This radar chart illustrates the weightage analysis used to select that land. Teams balance 5 competing constraints: the size and cost of the site, proximity to raw material suppliers and customers, existing utility infrastructure, and the availability of local manpower. This chart reveals a crucial metric: 17% of design errors leading to chemical accidents stem from poor spatial layout. Furthermore, gross plot area calculations legally demand exactly 33% of land be allocated to greenbelts to satisfy environmental agencies. Where you place the reactors versus the storage tanks acts as the absolute baseline safety shield for the entire facility. Phase 2 is the logic. Here, complex chemistry is organized into a universal visual language using 3 tiers of increasingly detailed diagrams. Level 1 is the block flow diagram, or BFD. It breaks down complex chemical reactions into basic unit operation blocks and quantifies the raw material inputs. This provides stakeholders with a clear look at the major operating zones. Level 2 is the process flow diagram, documenting the exact physics of process streams. It locks in fluid pressure, flow rate, and temperature. Notice the blue utility streams delivering cooling water, absolute necessities for thermal balance. Progressing from basic blocks down to specific temperature streams acts as a progressively tighter filter, locking in the required chemistry before anyone designs a single physical pipe. Level 3 is the piping and instrumentation diagram, or P&ID. This schematic serves as the ultimate operating Bible, explicitly detailing every single pipe, sensor, and valve mechanism in the plant. Engineers read this schematic using a universal alphabet of standardized symbols, categorizing everything from heavy mixing vessels and heat exchangers to individual flow valves and electronic sensors. This drawing carries immense legal weight. Under the rules of management of change, you cannot legally or safely alter the physical plant without first updating this exact document. The schematic enters Phase 3, the HAZOP study. Teams use structured guide words in a diagnostic table to intentionally break the design on paper. For instance, applying the word more to pipe pressure mandates installing a physical pressure relief valve. Exposing these flaws during a HAZOP study costs a fraction of what it takes to repair a physical plant after an industrial incident. With the design verified, process engineering serves as the central hub, feeding exact technical realities outward to coordinate the civil, structural, and procurement departments. This initiates Phase 4, execution. To track the physical build against the blueprint, project management relies on specific, measurable controls. The Gantt chart on the left visualizes time, enforcing a strict sequence of dependencies before heavy equipment arrives. The S-curve graph on the right tracks cumulative cost. By comparing the planned baseline against actual progress, management spots financial deviations instantly. Effective execution requires translating millions of abstract engineering hours into highly visible financial and temporal metrics. The final physical plant is confined by 3 rigid boundaries: strict legal safety acts, the rigorous neutralization of chemical effluents, and the growing requirement for renewable sustainability. Greenfield success relies on specific takeaways. First, layout dictates risk. Second, rigorous diagram logic saves capital by solving failures on paper. Finally, flawless process engineering drives the project. A successful reality requires a flawless blueprint.